Welcome to lecture number 24, and today we are going to discuss about the polynomial rings over unique factorization domain. We have already learnt about the unique factorization domain, and today we will try to answer two basic questions. So, let me first write down the questions that we would like to investigate in this lecture. So, the question 1 is, suppose you start with an UFD. So, let R be an UFD. Then the question is, if I consider the polynomial ring over R, that means polynomial ring over this UFD R, then whether this will remain an UFD or not. This is one of the questions that we would like to answer today. So, R be an UFD, then is Rx is an UFD or not? This is one question. And the other question is, so that means what we have to see, that if we start with a polynomial in Rx, then we have to see whether we can write down it as product of irreducible polynomials in a unique way or not. That is what we have to investigate. But since R is an UFD, we already know that if I consider that it has a quotient field, and we know that polynomial ring over quotient field are UFD. So, before addressing the next question, so let me just say that we already know that this Kx is an UFD where K is a field. But we do not know if we replace this K with any arbitrary unique factorization domain, then whether it will still remain UFD or not. But I know that polynomial ring over a field is an UFD. So, now somehow if I am able to connect or go from Rx to a polynomial ring over a field, then maybe I will be able to say something. But how to go from Rx to a polynomial ring with coefficients in a field? So, since R is an unique factorization domain, so it is of course an integral domain. So, in that case I can associate with R a quotient field, its quotient field. So, from R I can get say K, where K is the quotient field of R, quotient field of R. As R is an integral domain, so we have already seen the construction of the quotient field, and so I can associate with R, from R I can construct this quotient field. So, now I can have Kx, the polynomial ring over this field, and I know that this is an UFD. So, now I am in a situation that I have here Kx and here I have Rx. So, this Rx is basically sitting inside Kx because R is sitting inside K, and I would like to investigate. I know that this is an UFD and I would like to see whether this is an UFD or not. So, the thing is that if I am able to somehow connect the factorization of an element fx in Rx. So, fx is a polynomial in Rx. So, I can view this polynomial as a polynomial in Kx also, because R is a subset of K. So, then I know that this fx can be factored in a unique way into irreducible in Kx. So, fx can be factored. So, we know that fx can be written as say P1x into Prx, where all these Pix are polynomial in Kx. So, this is a unique factorization domain. So, all these Pi's are in Kx and it can have a unique factorization into irreducible. This fx can be written. But the thing is that whether from this factorization I can get down to a factorization in Rx or not, that is the question. So, if I am able to get down to a factorization in Rx from this one, then in a unique way, of course, then we can conclude that Rx will also be an UFD. So, the main question is, or the main thing that we have to understand is that of course we do not have any information about Rx, but the polynomial I can view it as a polynomial in Kx, and in Kx I know it is an UFD. So, I can factorize it in Kx in a unique way, and now if I am able to, starting from this factorization, write down. So, whether question is if we can write down fx as p1 prime x into pr prime x, where these pi prime x are in Rx or not. So, if I am able to do that, of course, if it is possible or not, that is one question, and then this can be done in a unique way or not, that is another question. So, all these questions are there, okay. But the thing is that we have to find out a way by which we can start from a factorization in Kx, and then we can get down to a factorization in Rx. Is it possible or not? That means we have to relate the factorization of Kx with factorization of Rx. If we are able to do that, then it will be easier for us to conclude that Rx will also be an UFD. So, in order to answer the question that I have asked in the beginning, we need to understand the factorization of a polynomial in Rx and in its quotient field, and what will be the relation between these two factorization. If we are able to understand it completely, then we will be able to answer that question. So, the next question that I would like to impose is the following. So, the question 2 that I would like to impose is that let R be an UFD, and K be the quotient field, of R. Let fx is a polynomial in Rx be a polynomial. Now, we would like to relate the factorization of fx in Rx with the factorization of fx in Kx. That means we would like to understand what is the relation between the factorization of a polynomial in Kx, because Kx is an UFD. So, we know that this polynomial fx can be written as product of irreducible factors, as a all these factors are in Kx, and from there can we write down a factorization of the same polynomial in Rx or not. That is what we have to understand. So, in order to understand that, let me introduce some of the definition that we will be needed in the rest of the lecture. So, let us start with the following definition. So, let R be an UFD. So, let R be an UFD. Then we define the content of a polynomial. So, the content of polynomial fx in Rx denoted by C of f. So, C of f denote the content. What is this content? This content is nothing but the GCD of the coefficients of this polynomial f in R. Okay. So, this is nothing but the greatest common divisor, greatest common divisor. We have already proved that in an UFD GCD exists. So, this is nothing but the GCD of the coefficients of fx. So, what do I want to mean? So, suppose if I consider, so just for example, suppose your fx is nothing but say this is 2x square plus 6x plus 8. So, you can see the coefficient. So, this is a polynomial over zx, okay, and you can see that here the coefficients are 2, 6 and 8. So, what is the content here? The GCD of 2, 6 and 8, which is equal to 2. So, this is what I wanted to mean by defining the content of a polynomial. Now, if the content of a polynomial is 1, then we call it a primitive polynomial. So, if the content of a polynomial is 1, we say f is primitive. So, this is the definition of primitive, and we will need this concept of content or the primitive in proving the factorization or in relating the factorization. So, let us first start with the following theorem. So, it says that if you have two primitive polynomials, then their product is again a primitive polynomial. So, let R be an UFD, and if fx and gx are two polynomials in Rx which are primitive, that means the content of both the polynomials are 1 individually. So, are primitive, then it says that if I consider the product of these two polynomial, say fx into gx, then this is also primitive. So, let us try to prove this. So, suppose I will first assume that this product is not primitive. Okay, so suppose fx into gx is not primitive. What does that mean? That means that content of this polynomial is not equal to 1. That means it is not the unit element. So, that means it should have a proper divisor. So, that means it should have, there will be some prime element or irreducible element, because in a UFD both are same, which will divide this content. So, let P be a divisor of the content. So, let P be a prime in R dividing the coefficients of this product, dividing the coefficients of fx into gx. So, that means all the coefficients of this product polynomial is divisible by this prime element p, because this is not primitive. So, it will have a prime divisor. So, now I will consider the following map. So, consider the natural map. What map I am considering? So, consider this map pi from this polynomial ring Rx to R quotient Px. How does this map is defined? So, pi of say some polynomial summation of a n x to the power n, this is a polynomial where these ai's are in this UFD R, and via this map pi I will send this coefficient will go to modulo this prime p. So, these I am sending it to summation of a n bar x to the power n, where a n bar is the image of a n in R quotient P. So, this is how I have defined, this is how I have defined this map pi. So, now if you see that if I consider this product f(x) into g(x), this polynomial. So, where does this polynomial will get mapped to? So, since we know that p divides all the coefficients of this, all the coefficients of this product, okay. So, that means whenever I will write down this under this map pi, all the coefficients in since all of the coefficients are divisible by p, so they will get mapped to 0 in R quotient p. So, this pi of this is nothing but this is, yeah, I can write it as f(x) into gx bar, which is equal to f bar x into g bar x, which is equal to 0 bar in R quotient px. But note that R is an UFD and P is a prime. So, R quotient P is an integral domain, and the polynomial ring over an integral domain is again an integral domain. Therefore, this is an integral domain, and product of two polynomial is 0 will imply one of them has to be equal to 0. So, since R quotient Px is an integral domain, then either f bar x is equal to 0 or g bar x is equal to 0. But what does it mean that f bar x is equal to 0 or g bar x equal to 0? That means all the coefficients of this polynomial f either divisible by p, or all the coefficients of this polynomial g is divisible by p. So, this implies that either p divides the contents of f, because content is nothing but the GCD. So, if p divides all the coefficients of f, then definitely p will divide the GCD of the coefficients. So, either p divides content of f or p divides the content of g. So, but what we already know is that f and g are primitive, that means their content are 1. So, it is a contradiction. So, which is a contradiction? Which is a contradiction. And the contradiction has occurred because we have assumed that f(x) into gx, this product is not primitive. That means we have proved that if we start with two primitive polynomials, then their product has to be a primitive polynomial. Now, using this fact, we will prove the following interesting result, which gives you the relation between the contents of two polynomials and their product. So, it says as a corollary, we can write down the following. As a corollary, we can write down that for f(x) and gx, two polynomials in Rx, we have that the content of their product f into g is nothing but content of f into content of g. So, if you see as a particular case, that previous thing follows from here, but we will actually be using the previous result to prove this corollary. So, let us see how the proof goes. So, suppose that this f(x) and gx, so let this content of f is equal to A and content of G is equal to B for sum A and B in R, because this is nothing but the GCD of the coefficients, and the coefficients are in R, therefore these contents will be elements of R only. So now we have to prove that the content of their product should be equal to A into B. So now since the content of F is A, so I can write down this F as follows. So I can write down this F as A times some F1x, and what this can I say about this F1? F1 will be primitive because I have already taken out the GCD. So, and moreover I can write down G also in the same way, where these F1x and G1x are again polynomial over Rx and both are primitive. This is important that these F1x and G1x are both primitive. So now if I apply this thing, then what we will get, since F1 and G1 both are primitive, so if I take their product, then by the previous theorem their product polynomial will also be primitive. So hence F1x into G1x is also primitive by previous theorem. So now if you look into the product polynomial, what we are having, Fx into Gx, this I can write it as A into F1x into B into G1x. So this is AB into F1x into G1x, where this F1 into G1 is primitive. That means what can I say about the content of this product Fx into Gx? The content will be equal to A into B. So therefore we can say that since this, so we conclude that the content of F into G is nothing but A into B, which is content of F into content of G. So we have proved this. Now the next result that we will need to prove the main theorem is the following. So it says that if you have two polynomials which are associates in the quotient field, polynomial ring over quotient field, then they will also remain associate in Rx. So let R be an UFD with quotient field K. Now it says that if I choose two polynomials Fx and Gx, this polynomial R over Rx are primitive and associates in Kx. So I am assuming that both these polynomials, so though these are polynomials over Rx, I can consider them as polynomial over Kx also, and I am assuming that in Kx they are associates. That means one of them can be written as some units time the other polynomial. Then this property that they are associates will be carried over to Rx also. So they are associates in Kx, then they are associates in Rx. So if two polynomials are associates in Kx, then we will show that they are they remain associates in Rx. So let us go through the proof. So, it says that suppose I am having that fx, since fx and gx are associates in kx, so fx can be written as some unit time gx, where this a by b is an element in k is the quotient field. So, every element will be of this form a by b, where a and b are elements of R and b is non-zero, because that is how we have constructed our quotient field. So, from here I can say that b into fx is equal to a into gx. This is we were able to write. Now, okay, so this much we are able to conclude. Now, it is also given that fx and gx are primitive. So, their contents are 1. So, since fx and gx are primitive, since fx and gx are primitive, so from here we can conclude that content of BF will be nothing but content of B into content of AF. So, which will be equal to of course B, and the content of AG is nothing but A. So, this much we can conclude from here. Now, since but this BF is equal to, note that this BF is same as AG. So, that means they are representing the same element, and since we are in a they are representing the same element in Rx, and since we are in a UFD and these contents are nothing but GCD of the same element. So, they are unique up to units, multiple of units. So, we can say that since in a UFD the GCD of the coefficients of a non-zero polynomial is unique up to multiple of units, up to units. So, we have that this A will be some unit times B for some unit U in R. So, this much we can say that A can be written as some units time B, because they are representing the GCD of the coefficients of the same polynomial. So, they will be unique up to multiplication by an unit, and now you can substitute here. So, what you are having here, fx is equal to a by b gx. Now, A is nothing but u times b. So, that says that it is nothing but. So, from here we can conclude that therefore, we can write down that this fx is nothing but u times gx for some unit u in R. So, you can see here that I have started with that fx here. You can see that I have started that fx is a some multiple of unit times gx, where this unit was in kx in the quotient field, and now I have concluded here that fx equal to u times gx, where this unit is now in R. That means I am able to prove that these two polynomials which were associates in kx remains associates in Rx as well. So, we can say that hence fx and gx are associates in Rx. So, this is what we have wanted to prove. So, now we have almost given all the required things to prove the main result, which will relate the factorization of a polynomial of Rx into product of irreducible polynomial in Kx with a factorization in Rx. So, once we will prove this theorem, then we will be able to prove that if you start with an UFD, then the polynomial ring over an UFD is still an UFD. So, I will stop here today. These are the references that I have used for today's lecture. Thank you.